Hello. Can you guys hear me now? Is everything fine? Guess I can't do much about the lag, but otherwise everything should be working fine. So shall we start? Okay, great. Hello everyone. My name is Gokul, and this talk is going to be about the anatomy of deep learning frameworks, or I like to call it as everything you wanted to know about deep learning frameworks, but were afraid to ask. So, before we start, a little bit about me. I'm currently a master's student in computer science at ETH Zurich, and I did my bachelor's from BITS Pilani, and I'm a contributor to Tiano now and then because grad life takes its toll. So there's that, and I'm working on right now. My area of research is more on using deep learning for astronomy and GANs. So you can find my work at the website's called space.ml, and this talk is basically an extension and more in-depth discussion of the topics I discussed in the blog article called The Anatomy of Deep Learning Frameworks. And I've posted a link to the slides on the events Facebook events page, so you can check that out, so you can follow it easily. Great. So now, what's this talk going to be about? It's basically going to be about understanding the internals of deep learning frameworks, and we're going to see that even though you have so many deep learning frameworks, they all have some common concepts that are applicable towards all. And once you understand them, it makes it easier for you to transition from one framework to another, and it helps you get up to speed much faster there as well. And you will realize that, like many things in deep learning, these concepts are not something new. They have been around since 80s or even earlier, and some of them are taken from compilers, so we'll see that as well. And finally, and I think this is the most interesting part, and how you could write your own deep learning frameworks, because by the end of this talk you will know that it's not a big deal, it's not magic, it's just plain software that you could do on your own if you have enough time. That's it. So next question is, why do you need to know this? So basically, the current all research right now is done using deep learning frameworks. No one says I got a good idea, things say I have a good idea, let me code it from scratch. No, it all happens like implemented on a deep learning framework. So, and deep learning framework like TensorFlow, Keras, Theano, they form the backbone of deep learning research, and it helps you and it sets you apart from other people when you understand what's happening in the background. And this is a quote from Arthur C. Clarke, that any sufficiently advanced technology is indistinguishable from magic. And yes, deep learning frameworks are pretty complicated pieces of software, and even though we use it on a daily basis, it's always magical when you think that some humans wrote this. So this talk is going to be about banishing that voodoo and showing that it's not that a complicated thing. And we'll find that these all have simple concepts that can be explained in an hour or an hour and a half. And but the caveat is that it's a bit complex to implement, and once you know it, you get more control over the deep learning frameworks. And if you figure out that, okay, I need to have some kind of a feature that's not supported by any of them, how do I make that on my own, or how do I use it on a special hardware? Because nowadays we're shifting over to mobile, and most deep learning frameworks don't support running it on mobile phones or, for example, Raspberry Pi. So if you want to do it for those, how are you going to do it? Okay, so this is just a slide to show that these are the common frameworks that are available. You have Keras, you have Chainer, you have MXNet, which is supported by Amazon right now, Theano from Mila, Yoshua Bengio's lab, TensorFlow from Google, Torch from Facebook, Caffe from Berkeley, CNTK from Microsoft. Now, basically, the question is, why do we have so many frameworks? If as I claim that they all do the same thing, why do we even have so many frameworks? Simple answer is, why not? I mean, even Linux, if you take a look at it, there's so many distros, but underneath they're all the same Linux kernel. So it's just to have more diversity, and also because these companies and organizations have a lot of resources and they have very niche requirements, it doesn't make sense for them to depend on an external framework and try to change their work and modify their work depending upon what the framework supports. So you can see that Theano from Mila, and if you see most work from Bengio's lab, it's implemented in Theano. Torch is from Facebook, and so most of the work is in Torch. CNTK from Microsoft. The ResNet paper was implemented in CNTK, and TensorFlow from Google. Well, most papers from Google and DeepMind are in TensorFlow. And the interesting thing is even though the concepts are same, each one of them does one particular thing very well. For example, Theano is known for its fast implementation of RNNs. Torch is known for its ability to give a very low level access to the deep learning to the neural nets, trying to change gradients and things like that. CNTK, as they claim, I've not tested it out, is good in scaling and it scales out very well, and so does MXNet. And TensorFlow is from Google, which is very flexible. It has APIs in Python, Java, C++, and they say it can be extended to other libraries, other languages as well. So it helps it's more flexible, and it has Android support as well. So there's that. And now the question is, are they really all that different? I mean, is it like apples and oranges, or is it apples and bridges comparison? So the answer is no, and that's what we're going to cover: how they're similar and how they're different. And you will see that the differences are not because they want to implement different concepts, but because they have difference in what kind of design choices they make. Okay, so next is what I'll call is bare bones deep learning framework. So any deep learning frameworks will have the following components. It has tensors, and don't worry if you're not comfortable with the terms. We'll go through them in detail. So it has tensors, it has operations on these tensors, it has a computational graph, it has an auto differentiation module, it has fast and efficient floating point operations, because all the tensors have doubles or floats as the data type, and you'll be technically working on floating points and not integers. So you need to be able to do it very fast and use your as hardware as much as possible. And then there's GPU support. I mean, current deep learning research uses GPUs almost on a daily basis. You don't get any papers on which say I ran the network on CPU and it's just too slow. And for this, we have libraries called BLAS, cuBLAS, cuDNN, which we'll cover when we talk about implementations. Okay, and to show that these are not just some abstract concepts, but are in different deep learning libraries. I have some examples. For example, in TensorFlow, you have the tensor represented through the tf.tensor API, operations to tf.operation dot whatever you want, add, sub, mul, and then you have the graph, computational graph represented as tf.graph, and autodiff can be accessed through the tf.gradients, and there are other other functions and objects and modules available in TensorFlow that you can look it up. And cuDNN, cuBLAS, these are packages that these link to. So when you look at the install notes of Ask, where they say how you could use GPUs, they'll tell you that you need to install cuDNN, how you could use them in TensorFlow. And the same things in Theano. Theano has some Theano.tensor. So if you take a look at any Theano code, they say import Theano.tensor as T, and then you see it being used multiple times in the code itself. And then you have ops where there's a lot of operations over there, or Theano.tensor.operations. So you can look them up. And these are all hyperlinks. So if you check the PDF, you can open up the corresponding documentation for that. And the graph is in Theano.gof, as they call it. It's the backend that they use for compiling .graph. Auto differentiation can be accessed by Theano.tensor.grad. cuDNN and cuBLAS, again, you can look at their installation instructions, and see that how they use these libraries for in the performance. Okay, so let's start with the first component, tensors. So what are tensors? They're nothing but mathematical objects, and so in a less abstract terms, they're just n-dimensional arrays. For example, a vector is like a 1D array because it has only one dimensions with some 10 numbers. A matrix is a 2D array which has rows and columns, and a tensor is basically a generalization of those two n dimensions, like 3D. For example, a 3D matrix it's actually a 3D tensor, 4D, 5D, and these are not abstract terms, but these are some things that we use on a day-to-day basis in tensor while dealing with deep learning networks, and I'll give you an example of that later on. So, and ND array, so tensors, if you've used NumPy, you would have seen that a NumPy.nd array that you use to create arrays. So this is a tensor implementation in NumPy, and like I said, it's the lingua franca in deep learning frameworks. People don't deal with the deep learning networks don't deal with images or audios. It's basically follows this kind of a flow. It starts with data. You have text, video, audio, and you convert them to tensors. You throw it in a deep neural net, and you get output tensors. Probably like after softmax layer, you have a probability distribution, and then you do a post processing on that and get out your results. So this allows a clean abstraction, and it allows your deep learning framework to be used in multiple scenarios. I'll come to what I mean by clean abstraction is that a neural net sees only tensors. It sees okay, 5D matrix of size 5 cross 5 cross 5 and so on with these numbers. It doesn't see okay, I'm getting an audio, I'm getting a video. So this kind of an abstraction helps you to try to use the same architecture or different use cases and different data sets. So that helps in portability in a way. So let's take a small example of how an image is represented as tensors. And okay, so what you have here is a bitmap image of I guess this is 270 cross 340 image, and this is in bitmap. That means it has three colors RGB, and it's of size 270 and 340. So let's just split it out from channels. So this is the red channel. So basically this is the intensity of the red color component of each pixel. This is the green channel, and this is the blue channel. So if you take a 3D RGB image like this, so it's like for each location you have three numbers which says the red intensity, green intensity, and the blue intensity, and this constitutes an image. So as you can see, it's a 3D tensor, right? So you can see here that row and column, it says the coordinate of the pixel. So you can see the third row and the second column, you see this number 111. This is nothing but the intensity of red, the intensity of green, and the intensity of blue. And so this is 3D tensor. So tensors are not an abstract mathematical thing that people came up. It's very real and people use it daily. And some other examples are videos. Videos are nothing but 4D tensors, because if you look at it, a video is nothing but stacks of images, right? And they're moving so fast that you see that see it as a video. So a video frame is an image. So the next the 3D is for each image, pixel intensity, and the fourth dimension is which frame of the video that you're looking at. So that's a 4D tensor. Words have something like a word2vec, which could be like a 200 dimension or 50 dimensional representation. And not sure if there was a talk on word2vec, but if you guys are interested, we can do it later. And characters can be represented as one-hot embeddings. Basically, one-hot embedding is like, so suppose if I have a text and you want to represent each character as numbers. So one way to do it is, let's assume that the text has only lowercase alphabets, so A, B, C up to Z. So that's 26 letters, and so you can have a 26 dimensional vector, and of all zeros. And for example, if the word is A, the first dimension would be 1, so it will be 1 followed by 25 zeros. Or if it's say Z, the last one would be 1 which was preceded by 25 zeros. So that's a one-hot embedding. Usually it's used for character representations, but it has its own pitfalls, because to represent one character you need to use 26 bits, which is a lot of wasted memory. And next is audio, which is represented as spectrograms or other ways. So basically spectrogram would be like for each at each time interval what frequencies are observed. So this is one way to represent audios. Another way would be to represent it in the frequency domain, which frequency is coming with which intensity at which time. So that's how tensors are being used. And if you want more information, we could have another talk on how to use word2vec or one-hot embeddings. Okay, so the next one is operations. So the first was tensors, and the next is operations. So by operations, I mean operations to be done on tensors. And if you think about a neural net, it has layers, right? So for example, a simple 3-layer fully connected network has 3 layers of sigmoids, for example, and each sigmoid layer is operating on an input tensor and throws out an output tensor. Okay, so these are that's how a neural network is implemented. It's implemented as a succession of operations, and of course, in a deep learning framework, we can always say, All right. Sorry about that. My laptop just hanged without telling me. All right. So we were at operations. Okay, so we are at operations, and like I said, neural nets are, if you look at it, it's just a composition of operations, and we could just say let the users implement. But the problem is that whenever users implement, they try to implement in a high-level language like Python, which, though it's easy to program, it results in suboptimal code where all the resources are not used properly, and another thing is it's prone to bugs. So there'll be this different developers will be trying to implement the same operations, and that would raise a lot of bugs. That would cause developer headaches, not just for the users but also for the developers who get their GitHub repositories filled with issues saying that, hey, I tried implementing this, it's not working, because and people raise issues saying that it's a problem with the library and not their implementations. And moreover, for example, if you want to use GPUs, then programming GPUs is a challenge of its own. So you'd rather not implement everything from scratch. And another problem is that, for example, if a user is writing a neural net for, say, a GPU, and then he wants to deploy it on Android or on a CPU machine, because inference is way cheaper than learning, he needs to rewrite this entire code again. So it's just a lot of work, and it's more difficult to extend to new hardware and software versions because the APIs change. And but so it makes sense to support basic and widely used operations. And by basic, I mean things like adding two tensors, subtracting two tensors, multiply, divide, exponential, log. And when I mean all of these are like element-wise operations. So adding two tensors just means that adding each of the corresponding components. Subtracting is the same. And multiplication, you could do matrix multiplication on tensors as well. So div, exponential, and logarithms are all element wise, and not just basic operations like this. Sometimes people, and actually a lot of people, all frameworks actually implement higher level operations like convolution, pooling, LSTM units, because all neural nets nowadays have these. And then for another one is the sigmoid function that I'll discuss next. So for example, this is the sigmoid layer. You have the hidden layer, which is basically the output of the previous layer, and you can see that the biases that you add, node 1, node 2, node 3, basically you're getting input from three neurons, and you have a sigmoid function over here, which is 1 over 1 plus e to the power minus w transpose x plus b, where w is the weight of the sigmoid layer, and x is these node 1, node 2, node 3 inputs, and b is the bias. So you have a multiplication over here, and then you have an output layer. You can run another sigmoid and then get the output. So sigmoid layer could be represented simply as 1 over 1 plus np.exp for this expression, which is basically the sigmoid layer expressed as numpy, one line of numpy. So it's always pretty cool. NumPy is pretty cool library because such a complicated thing. If you were to implement, then you have to do all the dot product. You have to do the matrix transpose on your own. But in NumPy, it's just one liner, and it's blazingly fast. So that's about operations. The next topic is a computational graph. So a computational graph is nothing but a combination of multiple operations. So like I said before, neural nets have basically an op after an op after an op. So computational graph just represents the entire collection of operations and the relations between them in a graphical way. So and this is similar to abstract syntax trees. Like I said earlier, deep learning has a lot of old wine and new bottles. So this again is from compilers, and if you take your compilers books and go to abstract syntax trees, you'll see the exact image that I'm going to show you there, but in terms of compilers and not in terms of frameworks. So this is an example of a computation graph. So suppose we want to compute E equals C times D, and we have C is computed as A plus B, and D is computed as B plus 1. So, and these are the inputs A and B. So C, to compute C you need A and B, and then to compute D you just need B, and then to compute E you need C and D. So in a simpler example of how this can be seen in a neural net is, just consider this line and let this be a sigmoid layer. So A times a sigmoid is the output, for example. So this is how you could visualize neural nets as computational graphs as well. So the question is, why do you need it? Like, okay, it's a graphical way to represent operations. It helps you visualize and things like that. So that's a good to have feature. Why should it be a core part of the deep learning framework? The reason is that it helps you get a bigger picture of the network. And why do you need it is, it helps you run something called as auto differentiation on the network. I'll come to this later, but basically auto diff is how back propagation is run on networks, and it helps in allocating resources to get the best performance. For example, if you have a CPU and a GPU, so the question is basically which operations do you put on GPU, which operations do you put on CPU, or in cases where you have multiple GPUs, so the question again arises, which operation do you put on which GPU, and when do you organize, for example, when do you say, okay, this operation should be done, then next is how do you schedule operations. So all this can be done only if you have an idea of all the operations that are available, that are needed to be done. So having a bigger picture helps you allocate resources much better, and it also helps in doing some optimizations. Basic, for example, if you have let me go back to the previous slide to give you an example. Okay, for here, if you look over here, D is just B plus 1, and so let's say if you have another layer, another operation here, okay, so let's say you have another operation here which says B plus 1 again. Right, so if you have B plus 1 over here, it's, you see that these two operations are wasteful. You can just combine them together to say D equals B plus 2. So this is a kind of optimization that you can do only when you have a bigger picture. You cannot have this if only you know which operations are doing. You need to have a bigger picture to be able to do things like this, like reducing two additions into one, and other examples as well. And it helps to have a encapsulation and a clean API. For example, what I mean by encapsulation is that when you're doing inference or learning, you do it on the entire network. You don't do it on each one of the layers. So it doesn't make sense. It doesn't make sense to just show different layers, expose them, and tell the user to figure it out itself. It makes more sense to grab them out in a nice computational graph object, and then call in method on that, say graph dot, for example in Keras you have graph dot predict or graph dot train on batch, for example, which does this for you, the entire thing from start to end and doing back propagation. So this helps in having much cleaner code and much easy to use APIs. And like I said before, it also helps in orchestration of operations, because since there is like a sequential way of things happening on the graph. For example, op2 requires the outputs of op1 to do its work. So that means you need to schedule operation 1 on the GPU first, then get its output. Alright, so Malay asked a question that why should it be auto differentiation and why can't it be symbolic differentiation? That's a good question, and I will come to that later. I'm just giving you an idea of what to do here, what is there in the deep learning frameworks, and then I'm trying to justify why these are there and why only these are enough to have a bare bones deep learning framework. So coming back, orchestration of operations. So if op3 requires the output of op2, you need to first schedule operation 2 on a GPU and get a notification that it's done before you can run op3. So all this can be done only when you have a bigger picture. You cannot do it if you have just the operational view of the things. Okay, so now the most important thing: how do you train neural networks? How do you run back propagation on these? And this was what Malay had asked. There are two things called auto differentiation and symbolic. So what we want to do is we want to have something which is more general than back propagation, because if you've read any deep learning books or machine learning books in general, they just simply say, oh, we have a feed forward network and we do back propagation on this. But current architectures are much more complicated. There are branches going out. For example, in GoogleNet that we had a talk about later, they're skipping layers, and there different things that is difficult to express in terms of back propagation, but it's easy to express in terms of computational graphs, because you can see that as a computational graphs, and then we could do calculus on that, which we'll be talking about next. So what we're doing is calculus, as in computing gradients in the computational graph. And one common thing that we do is called chain rule, which I'll show you the equations for tomorrow, in the next slide. And there are two things with when you want to do differentiation. There's something called symbolic differentiation and something called auto differentiation. So what symbolic differentiation is to analytically find the gradients of each operation, that is by using chain rules. For example, if we have z equals f of y and y equals g of x, so you can look g as operation 1 and f as operation 2, so you can write z as output. So this would be z would be f of g of x, so that means it's something like a two-layer network. And if you want to find the gradient, this is how you do it. The derivative of z with respect to x is derivative of z with respect to y, because z is the input of z is y, and then derivative of y with respect to x, because y depends on x. So this is how you do it. But the problem here is that you cannot calculate it for all functions. In some cases, it's just too difficult because you have fancy integrals, for example, in terms of convolution. And in some cases, it's just not possible because, for example, in RNNs, it's looping over and over again. So how do you calculate the gradient? I'll come to these later. So symbolic differentiation, though it's nice to have, it's cannot be used. It's not used for all operations, and not just some fancy operations that people can come up, but even with day-to-day, even with common generally used deep learning operations like convolutions, it gets difficult. So the alternative is called an auto differentiation, which is just another approach to tackle the chain rule. It goes like this: you compute the gradient for each operation. For example, in here you just compute f dash of y, g dash of x, and again I'll come to how you compute that. And then when you traverse the graph, you just collect the gradient for each operation. We'll use the example that I discussed earlier, and I'll show you how the gradient flows. And so what you do is you go traverse the graph, you get the gradient, and as per the chain rule, you have to multiply them, right? So you get it, multiply, and then you have then that's your back propagation, which works in general. It doesn't worry about whether you have loops or skips. You just follow the links, you collect the gradients, and you compute the difference, and you do back propagation. And it can be done in both forward and backward directions, depending upon your use case. By forward, I mean from input to output, and by backward, I mean from output to input. So the backward direction is from where the name back propagation came from. So going back to our example from earlier, It's C equals C times D, where A and B are inputs, and C is computed as the sum of A and B, and D is computed as B plus one. So these, you can see from this link to link, you can compute the D partial derivative of D with respect to B. In this link, you can compute the partial derivative of D with respect to E, and in this link you can compute the partial derivative of E with respect to C. So while traversing through this link, you only need to know these partial derivatives. You don't need to know partial derivative of D with E with respect to D, this one, because it does the gradient, the term that we use is the gradient doesn't flow, that gradient doesn't flow in this direction. So the partial derivative D with respect to E flows only here, not in the other way on. So as you can see, this is a simple example, but you can realize that this can be generalized to much more complicated neural networks, and that's why we use auto differentiation over symbolic, because it's just easier to scale as well as easier to compute. However, if you are, although there's still one thing that's left, how do you compute the gradient for each operation? Because we talked about collecting the gradients, but how do you compute this delta? Sorry, how do you compute this delta C, del C by del A? Because that's still a challenge. So for this, we have simple. If you have, it's easy to compute. Then you just calculate the gradients, or if not, you have other ways to do it. So to do that, let's take a small intermission and have an aside called subgradients. So what subgradients are is that subgradients usually come in cases of ReLU, which is rectified linear unit, or leaky ReLU, and there are other variants as well. So the problem is that these are not differentiable. For example, if you see over here, right, if there's this inflection point, so if you're trying to calculate the gradient over here, it's not possible analytically, even if you use the basic definition of a gradient of a derivative. It says derivative does not exist over there. Similarly here as well, you see that there's an inflection point. So when you're approaching from the left, you'd say what it was x ai times xi. So the gradient from the left side is ai, while coming from the right side you'll say the gradient is 1. So these two do not converge at x equals 0, and you say the gradient doesn't exist. So what we do instead is have an approximation. Like I said, we don't have we can't differentiate at x equals 0, so you approximate it, and the way that you do it is called a subgradient, which is basically an approximation to gradients, and it gives the greatest lower bound. So let me show you what that means. Suppose this is a function that you have. Okay, this looks like a piecewise continuous function with inflection points over here. Let me just change the color. Green seems good. So you have inflection points here, and here. So when you want to compute the gradients over here, you cannot do it analytically, because the derivative is discontinuous. So what you do instead is you have a line like this line, for example, which at x0 it's equal to the function. So let's say this is g. So g of x0 equals f of x0. Okay, so at this point a subgradient satisfies the property that if g is subgradient, then at x0 it has the same value as the function, and also on other points it's always strictly less than the function. So if you can see at this point, g has a lower value than f. Similarly over here, g has a lower value than f, and so on. So that's a definition of a subgradient, and I'm not going into the proofs, but this is a good approximation of approximation for gradients at a point x0. So that's how you compute gradients for non-differentiable functions. And even for convolutions as well, what they do is they convert it into they do a Fourier transform, and then it's easier to differentiate over there. But without going into much of the mathematics, that's how they do it. And another interesting thing is how do you compute gradients for RNNs, or recurrent neural networks. RNNs basically have the output of the same layer as the input, but in the next time step, so to speak. So the function is something like the output at t plus 1 is a function of some inputs as well as the output in the previous time step. So the problem is, how do you run back propagation on this? If you represented this as a computational graph, you clearly see that there's a loop. So you just loop and loop and loop and loop, and you just compute gradients so much, and what happens is you keep computing small, you keep multiplying small numbers, and this either small numbers or large numbers, and then this results in something called as exploding gradients, wherein it just keeps going so much that a floating point number cannot hold the number, it just overflows, or it just you multiply small numbers like 0.001 or 10 to the power minus 5, you just keep multiplying it 5 times and it becomes 10 to the power minus 25, which is no longer which may not be representable anymore in a double precision number. So what you do is you do something called as loop unrolling, and this was a image that I took from Christopher Ola's blog post. So what you do is, if this is the RNN layer with the loop over here, so what you do is you unfold it so that at t equals 0 the output is h0, and at t equals 1 the inputs are x1, and the h0 over here, basically you can show it like this, and the output is h1, and then you roll it up to, say, instead of time, you can roll it up to infinity, right? Because it's just, if you have infinite time you can keep rolling it, but let's say you can roll it only up to, let's say, 5, and you hold it there. You'll say, okay, this is my RNN, and I'm going to unroll it to 5, and I'm going to keep it like that, and then you compute the gradient on that. You can compute for here the gradient, it flows like this, right? So to see how gradients flow, you just reverse the directions of the arrow. So the gradient from ht flows like this, and so on. So you can you can unfold it to, say, only 5 times and say, okay, this is how I'm going to compute my gradients. This will not be the exact values, obviously, because you're, instead of doing it for infinite, you're just approximating with a finite number of unrollings. But like we did in subgradients, there are results that say, okay, this is good enough with a certain epsilon tolerance, which means that the actual gradient and the computed gradient differ only by epsilon, which is okay, because there is a notion, there's a small amount of stochasticity in the way that we learn, so we can tolerate small deviations. So are we done with just unrolling it, say, 5 times, and are we done? No, we still can cause underflows and overflows, because let's say if you have only just 5, and let's say the input gradient is 10 power minus 20, okay, so if you do that 10 power minus 20 times 10 power minus 25 times, you get 10 power minus 100, which again can cause underflows, or if it's 10 power 20, it can cause overflows. So the loop, by unrolling, we resolve the looping issue, but we still haven't resolved the underflows or the overflows. So what they do for this is called gradient clipping. What happens in gradient clipping is, basically, you allow numbers only between you say that the gradient g can be only less than equal to x0. Not x, because x is our input, and a2. Okay, so this is called gradient clipping, Okay, I can't erase. Sorry about that. So this is called gradient clipping. So whenever the gradient goes below A1, it's pushed to A1, and whenever it goes above A2, it's pushed back to A2. So that it's always between A1 and A2, and these two numbers are chosen in such a way that they cover a large range of gradients, but still being represented by double precision numbers. So that's how you do back propagations on RNNs. So these two. Okay. Just a moment. Alright, these two are the way that you can. These two are the ways how you can compute not so straightforward ways of calculating gradients. Now that we've talked about conceptual ways of how deep learning frameworks work, now it's time to get dirty with the details and actually talk about how these are implemented. So, as a quick recap, these are the components of a deep learning framework: the tensors, their operations. There's a computational graph. There's auto differentiation, which is what we talked just before, like how do you compute gradients on a computational graph. And then you have a fast and efficient floating point operations and GPU support, which we'll be talking about now. Okay, so before we go, a fundamental question that we need to answer is, how do we represent, say, tensors, or how do we represent operations? Do we represent them as functions, or do we represent them as classes? So representing as functions makes more sense, because we are taking in an input, we're computing something, and we're returning back a value. That sounds exactly like a function. What a function is, perhaps that's the definition of a function from CS 101. And another advantage is that there's lesser memory footprint, because you're not storing anything, you're just taking something, computing, and sending it back. And there's a logical mapping between drawing it as a sigmoid function to a sigmoid function implementation. But however, if you were to represent operations as classes, it helps in better encapsulation. So by encapsulation, I mean you may need other information like shape. What's the shape of the tensor, so that maybe you need to check if it's only a 3D tensor or a 4D tensor, because you may, for example, convolutions, usually you do it on 2D inputs or 3D inputs. You can't say give it a five dimensional tensor and ask it to go figure it out. So you may want to do things like what's your shape and size. And also, if you represent operations as classes, you can have two functions inside, one for computing the forward operation. Basically, in case of sigmoid, for example, if I give you an input, say let's call that function as dot apply. So sigmoid dot apply of x will run the sigmoid on the input tensor x and give out a value. And if you want a backward operation, or if you want to compute gradients, you can have another function which stores how to compute the gradient for that operation. And also you can have something like an abstract class, which has functions that any operation has to implement, which you can inherit and then do things. It helps in scaling and extending frameworks. For example, if you want to write your own operation, how do you make sure that your operation works well and works well with the other operations in the framework? So using an abstract class helps you to have contracts saying that this operation will have a function called apply, which will apply the operation, or a function called grad, which will run the back propagation. But however, there's a catch that classes have a higher memory footprint, because these will be allocated memory on the heap, and this will take up more memory than having a function. But however, memory is cheap. Dev time isn't. So it's easy to get extra 16 GBs of RAM or 1 TB of hard disk maybe caches are a bit expensive, but still. But however, getting an extra developer is much more expensive than getting a extra RAM. So it's better to have, even if it's their higher footprint, it improves developer efficiency. So classes are for the win. Even though functions make logical mapping easier, functions help. I mean, objects help to have a better abstraction, and it helps improve productivity. Okay. So now that we have agreed upon the fact that all the operations has to be objects, so naturally tensors should be also objects, because those are an array. You can't just given it's you cannot have a raw API for tensors. So even tensors are objects. And what does an tensor object need to do? It needs to be able to convert data to tensors and back. And what I mean by converting data to tensors is, for example, I showed you the example of the image early on. For example, if you have an image, you want to be able to convert it to tensors. Let's say call it as t, and then you need to be able to convert the tensor back into images. For example, if you're running a GAN, generative adversarial networks, and the output would be a tensor. So how do you change it back to an image so you can see what's happening? So it needs to be able to do that. And since of course tensors are ND arrays, it needs to have an efficient way to store arrays, not as, for example, arrays or linked lists, or for example, it might need a it might be a sparse matrix where a lot of numbers are zero. So you need to have efficient ways to store the matrix such that the memory that you use is minimized. And it needs to have other metadata, something like shape, type, average, min, max. Let me just remove the marking. So it needs to have metadata types like shape. What's the shape of the tensor? It's 5 cross 5 cross 5, for example, is the shape. And what type are the data? Is it floating point, or is integer, or is character? And for you could have other frequently used metadata like average on minimum and maximum. For example, average, you could have average for tensors because in images, because one of the common pre-processing steps that you do is you take images and you minus the mean across all the images, so that it's between a fixed value. I mean, it's in a finite range instead of expanding in the entire range. So this is one of the common pre-processing steps that's used in CNNs, like subtracting the mean. So it's better to have the mean for each of the tensors that you could use later on instead of computing it again and again. And of course, min and max if some other use cases might need it. And it has to support things like splicing and views. What I mean by splicing is, like in Python, you can get say phi colon, sorry. Okay, splicing would be like, sorry about that. Okay, splicing is something like accessing a subarray of one subarray of the tensor or a subtensor. For example, if you have an array of 10 elements, and if you want to access from the second element to the third, to the to the fourth element, or something like that, it needs to be able to support the angular braces that you find in NumPy and by general Python arrays. And the difference between splicing and views is that splicing, when you say in an array with 10 elements, if you want to splice it between the second and say the eighth, it creates a new array of the elements from the second to the eighth elements and gives you back. Whereas view just gives you a view, in the sense that the background of in the backend, the object is the same. It's just that it's a new meta tensor which lets you access from the second to the eighth element alone. So that's the difference between splicing and views. Uh, just a moment. There's a question from Pranay Mathur. He asks, can you give an example of derivatives involved in BPTT? What's BPTT for me? So yeah, I'm just asking for a clarification on that, but all right, it's back propagation to time. An example would be in just an LSTM case where you can just a moment. Okay, so BP. There was a question which asked, can I give an example of a derivative involved in BPTT? And BPTT is back propagation to time. Yes, you could have like RNNs themselves as like running through time. Like the second character could be assumed to come in the next time step. So and then when back propagation, then there is just I can show you let me just show you the unrolled thing. Yeah, hello. I'm just checking the live feed. Yeah, it's saying that it's not healthy. Or should I restart or? No, there's nothing else running on the machine. It's fine now, or is it still buffering, or? Okay, so shall I continue? Okay, thank you. Okay, so going back to the question, back propagation to time, uh, I'll show you that example right now. Like we had the example on back propagation to on RNNs, right? So you can use this for example, xc instead of x0, you can always say it's the input at t equals 1. So this can be represented as t equals 1. This is T2, T3, and so forth. And back propagation over here would be basically running as back propagation over time. It's the same layer, but when you unroll it, it's like at different time steps. Okay, so that's one simple example of BPTT. So, and continuing where I left, the tensor objects, yes. So what does a tensor object consist of? It consists of an efficient storage of arrays along with metadata such as shape, type, average, min, max, and it should support splicing and views. And also, like I discussed, it should have support for sparse matrices. What I mean by sparse matrix is, if you have a matrix, and if a significant number of elements are zero, and then it's called a sparse matrix, because you don't have to store those zeros, you just have to store the non-zero values and say any other element is zero. Now the question is, how much is significant? That depends upon the use case. So in these cases, it doesn't make sense to store all the zeros. It makes sense only to store the non-zero values and their locations. So that's a way for that's called the that's a sparse matrix representation, and it is common in neural networks whenever you use things like ReLU or max out layers. Most these in ReLU, if you remember, the activation for any inputs less than zero is zero. So you can imagine that on an average, if half the inputs to the ReLU layer of negative, then the half the outputs would be zero. So in these cases, we need to have support for sparse matrix representations and how to run operations on the sparse matrix, because a simple matrix multiplication which access the different rows and elements won't work here, because when you access a row and a column in which the element is zero, you need to handle it saying that, okay, this is a zero element and I need to send back zero. And then you need to have something like integrity checks, GPU transfers, and compression. Integrity checks are basically, suppose if you're deploying this on on a commodity cluster wherein there are multiple systems running the neural net, and you need to transfer the tensors from one node to another. So it's possible that the data can get corrupted during communication. So you need to make sure that what I sent and what I received are the same. People do it using like MD5 hash sums, things like that. So depending upon what you're building this for, you might need to have support for integrity checks. And even, for example, when you're using GPUs, you need to transfer the data from the CPU to the GPU, run some computations, and get it back. Because when you code something and when you start, say, I don't train.mod.py, it means that the program starts on the CPU, then it creates the objects and then sends it to GPU. Then it sends, okay, I need to do these computations on the tensor, do it, and once that's done, you take it back. So it needs to have support for transferring it to GPU and back. And like always, compression is needed when you want to talk over network or any kind of communication. It's good to have compression to reduce the overheads of communication. So these are just what tensor objects should contain. And another point that I want to make here is, this is not an exhaustive list, nor is it like a necessary list. What I mean by it's not an exhaustive list is that these are not the only features that a tensor object must have. There might be other features that you want to have it depending upon your use case. And also, you don't need to implement all of these. For example, if you know that you're going to run it only on one GPU, you don't have to worry about integrity, or one node with a single GPU, you don't have to worry about integrity checks or compression. And if you're okay with letting since you're working on small neural networks, if you're okay with wasting memory in terms of sparse matrices, you can avoid this as well. So it's just just a list of things that's good to have and that any good deep learning framework should have, but it doesn't mean that all frameworks will have it, or these are the only things that are there with all the frameworks. So I just wanted to make that point here, because when we discuss other classes and object as well, you'll see similar lists, and the same holds there as well. So the next is the operation class, or op class for short. And the first thing is it should have input sanity checks. For example, if you are expecting only floating point inputs and you get an integer, you might want to throw an error saying that you got an integer mere tensor instead of floating point, or you can just typecast it. Or if you're expecting only a 3D tensor and you get a 5D tensor, you want to throw an error saying that too many dimensions, or if you get a 2D tensor, you can throw in exception saying that too little dimensions. Excuse me. And then obviously it needs to have an optimized implementation, and by optimized it could be like should be optimized on CPU as well as on GPU. So depending upon the use case and how you implement it, the optimizations might vary. And of course this that was for the forward propagation, and for the backward propagation you need to have a method for using which you could compute the gradient. And again, another thing is, in you can, given an input size tensor and you know your operations, you can predict the output tensor's shape without actually performing the operation, because operations are deterministic. And you can say that, if for example, let's take matrix multiplication as one of the ops. So if you have let me see if I can write it here. Okay, so if you have an n times p matrix as your input, and you have a p times say m as your weight. So you want to calculate, say for example, w transpose x, which is just, this is a linear layer. So if you want to, and you know that, let's say x is p times m, and the, okay, so can it be, yes it can, and w transpose is n times p. Now without actually computing the product, let's say if this is y, I can say that this would be n times m. Okay, I don't have to compute the matrix product between w and x to get y and then see its dimensions. So when you know the shape of the output tensors, then you can say that you can use this for sanity checks over the network. For example, if you describe only the shape of the input and then you run several operations, and then later on you've done, say for example, 4 operations, and the 5th operation needs to do a sanity check whether I'm getting a reasonable, when expected as shape, it can just get the shape of the output tensor from the 4th operation instead of actually running a computation. So this helps in reducing errors and doesn't add much in terms of memory or computation time. Okay, and apart from this, like I said, we needed optimized implementations. Usually implementations could be done in C++ or CUDA. For example, in Python, in Theano, what they do is, for CPU bound operations, they just have it in implemented in Python but using NumPy, which NumPy again uses something called Cython and C, which is pretty fast. Or if you take TensorFlow, their backend is written in C++, so which is again fast. And if you want to have GPU support, you need to write it in CUDA. So usually you have implementations in one for CPU and one for GPU. So there are objects, there are methods which have implementations in C++ and CUDA. And then next, if you remember our discussion from the computational graphs, we said that we need a computational graph to efficiently allocate resources. So, and each op can say, hey, I need to run on GPU because it's much faster for me to run on a GPU than on a CPU. And some operations can say that, okay, it's I mean, the difference between running on a GPU and CPU is not so much, so you can allocate me on a CPU. So this could be just a Boolean flag saying, is GPU yes or no. And also another thing to have is to have references to the parent and children ops. So if you look at a computational graph, it's something like this, right? So could be more than one. So it comes from parents, and it could go to children as well. So this operation, this op class should have reference to the parents, like from where are you getting your inputs from, and also from to its children, where are you sending your where outputs to. So this helps in having the representation for a computational graphs, and and for back propagation, forward propagation as well. So forward propagation, you need to know which nodes take your outputs so that you can send them there. And for the backward propagations, you need to know where you got your inputs from, so that you can flow let the gradient flow over here and over here and here. So these are what should be there ideally in an operation op class. And like I said before, this is not an exhaustive list, nor is it a bare minimum. It's a good to have list. And next, for the computation graph object, the components that you need, like I said, it's a container class which has references to the different uh, ops which are in the network, and it has reference to ops and the input and the output tensors. It should have graph traversal routines, both forward and backward, forward for inference and backward for learning. And it should be able to say that, okay, how do you get a lock on a GPU, and how do you assign tensors to there and the operations over there, and how do you get back, how do you free the memory from GPU or from other nodes. And like I said, it should have methods to send tensors over there and get back results. So these two are different because in device allocation, you need to first get a lock on a GPU. By getting a lock, it's a way of making sure that no other operation is working on the GPU right now, or no other operation data is being stored in that part of the GPU. So once you get a lock, then you send inputs, the tensors over there and the operations over there, and you let it run, and you get back the outputs from there. And a method to run autodiff, which traverses the graph and collects the collects a gradient from each of the operation, and then tells it, okay, your gradient, since I got the errors from your children as this should be your gradient, and it updates the weights as well. Okay, so these are what should be there in a graph object. And finally, the auto differentiation. This is a common mantra in software development, is don't reinvent the wheel. Auto differentiation is not something that's unique or new to deep learning. It's been used in other places as well. For example, in fluid dynamics or CFD, computational fluid dynamics, where they're trying to simulate differential equations. They need auto differentiation tools, and therefore there is a huge list of auto differentiation modules that you could just plug in, and you could just call routines from there and get done. So this is one list that I found, which has not just for Python but for multiple languages, the auto differentiation modules. And just some of the examples that I saw in Python that I felt were good, and I've spoken with people who have used themselves, and I've tried using them myself, and they were nice. So CGT is Computational Graph Toolkit. It's from Berkeley, and it has a very nice interface for auto differentiations, and it's pretty fast. And AutoGrad is from Harvard, and it's also a pretty good toolkit as well. So you could check them out if you want to do it in Python. And TensorFlow and Theano and TensorFlow use their own implementation of auto gradient, because they realized they didn't want to use these, and they'd rather implement it on their own because they have the resources, and they'd like to keep their framework as a whole component instead of trying to rely on other modules. But if you're doing it on your own as an individual developer, then it makes more sense to not waste time trying to implement it on your own, but instead use libraries. And the next question is, how do you support multi-cores, GPUs, and embedded? Because deep learning today is run on a huge variety of hardware, right from your laptop PCs to JBOG. JBOG stands for just a bunch of GPUs, which was released recently by Facebook as their next generation GPU server, and I think it has 8 Titan X's. So how do you run it on that, and or on some small device like a Raspberry Pi or your phone? So how do you support these? Because programmers use your deep learning framework, and it has to compile to code which can run on laptop PCs as well as server systems as well as Raspberry Pis, and these are completely different hardware, and each have their own strengths. For example, strengths and weaknesses. For example, laptop is portable and usually power is a concern. JBox don't care about power, and they're extremely powerful, and they have a lot of memory and compute. So for example, you might not have to worry about having a sparse representation because there's enough memory, and Raspberry Pi has compute as well as power constraints. For example, you cannot get more than so many watts on a Raspberry Pi, and you cannot make it overheat. So there are constraints that you need to take care of, things like power efficiency, parallelism in terms of how do you use multiple GPUs or multiple cores of your PC. For example, almost everyone today uses a multi-core processor, right, in their laptop. So how do you make use of all the cores available instead of just one? And if you're using on a cluster scale, how do you make sure that you reduce your network communication, and how do you handle things like uh, integrity, basically, like how do you compute, make sure that the data that you send is what you received, it was the data that you received is what the sender sent, and there's no corruption on the way. So you need to you need to think about these depending upon your use cases. And for example, I like this example a lot because if we take the Raspberry Pi, it has low power and memory. I think latest was 1 GB. But the interesting thing is it has a GPU and it can support HD video. And there was one blog post which talked about a guy who ran deep learning networks on Raspberry Pi, but he had to go into the assembly and write his own drivers to make sure that the GPU on the Raspberry Pi can be used, because it's not an NVIDIA GPU, it's a Qualcomm GPU, I think. So you need to go through that and figure out how you can use it. So we need to make sure that these multiple hardware can be supported opaquely, because the user should not be worried about what hardware am I running. The deep learning framework has to worry about, okay, this is what I have, and this is how the restrictions that I have, and how should I use it. Okay, so this is another constraint that that factors into the design of the frameworks. And as you can see, there's a lot of choices over here, and depending upon your choice, your complexity of the framework increases or decreases. Okay, and another way to do it, another thing is that to use hardware efficiently, there's another trick that people use. They use optimized numerical libraries, because like I said, thanks to the abstractions that we have at the bottommost layer, it's just different tensors. There's some matrix operations, and you get an output tensor. So these tensors and matrices come in physics simulations, mechanical engineering simulations, civil, whatever. So then people have been working on this since computers came out, and so they're very optimized numerical libraries that you can exploit to have better performance and optimizations. And these are called BLAS or LAPACK. BLAS stands for Basic Linear Algebra Subprograms, and LAPACK stands for Linear Algebra Packages. So these are just collections of routines which are routines which are commonly used in linear algebra use cases. For example, matrix exponentiation, matrix transpose, or maybe finding the eigenvalues, things like that. So these are highly optimized, and it's usually written in Fortran or C. And you can you can send it the inputs, you can call the functions, get back the outputs, and you can be assured that it's one of the fastest implementations around. And in fact, it's sometimes people you write even assembly because that's how you can get the most out of a system. You write it in Fortran or C, which are low level languages, but if you want to squeeze as much performance as possible, you need to write in assembly, and some of these are so these are pretty good libraries. And these have been in development since 80s, and it has grown till then to support multi-core as well. So usually your frame, when you're implementing a framework, it would be like you have an op object which gets inputs, and then when it says I want to do the operation, it calls routines in BLAS or LAPACK with the inputs and gets back the output. It seldom does it on its own, or it uses NumPy, which in turn calls BLAS. Okay, and like I said, NumPy uses them, and we use routines for matrix operations instead of coding them, because again, if you were to code it on your own, it might be highly inefficient, not worrying about locality or caches and things like that. So an extension to this for GPUs is CUDA and cuBLAS. So because BLAS and LaPlac that I spoke about in the previous slides are like CPU only hardware, I mean CPU only library, and these have not been extended to these have been expanded to the GPUs, NVIDIA cards particular, and through libraries called CUDA and cuBLAS. So CUDA is a GPU programming API. It exposes the GPU into GPU memory and the operations that you can have as an API, and you can write it as a C code or C++ code, or in Python through PyCUDA. You can write the code over there and compile it using NVCC instead of GCC, and you can run the code on the GPU instead of on the CPU. And it's very low level, wherein you have to do your own memory management. By memory management, I mean you need to allocate your own memory, you need to store your own values, run the operations, and then once you've got back the data, you need to free the memory and things like that. So a lot of low level implementation level details are left to you, and because of this, if you do it in the wrong way, it can lead to actually reduced performance than on a CPU. For example, if you just keep moving data to and fro your graphics card, then what happens is the data transfer becomes the overhead, and you cannot and all the performance gains that you get by running it on a GPU are lost. So instead, what they did was they came up with again BLAS routines, but for the GPU, and it's very similar to the BLAS API. For example, if you had a function called mmmul, which refers to matrix multiplication in BLAS, CUDA BLAS would have a similar method which called cummul, which just means CUDA matrix multiplication. So it helps because they have such a similar API. It's very easy if you know BLAS to just port it. It's just a matter of adding a cu in front of the cu in front of the BLAS, even in your routines, and you're done. And if you're not really into this proprietary thing and not really wanting to stick to only NVIDIA because you feel it's like a monopoly, there is another alternative called OpenCL, which is in development, and it works on both AMD and NVIDIA and other graphics card available, but it's in beta form, and not many people use it, and it's still in development and not as performant as cuBLAS. But as far as I know, Theano has partial support for it, and they're working on making sure that OpenCL can that they have better support for OpenCL. So that's something you can check it out if you want a completely open source deep learning stack. Okay, and finally, this is something most people would have heard of, cuDNN. It's basically a library with deep learning primitives. What I mean by this is that it has, instead of, for example, for a sigmoid layer, instead of calling matrix multiplication of with W transpose X, then an exponentiation and all that, it has everything covered. It's a higher level API, and it's built on top of CUDA, and it has functions called like cont2d and the latest cuDNN supports LSTMs as well. So these are higher level APIs that you can call, and actually most deep learning frameworks use this in the background. So again, if you go back to the installation instructions for both Tiano or TensorFlow, they have instructions on how to use cuDNNs and in the background. Basically, you install it as a library, and then it'll take care of it on its own. And like I said, it's high level, and it's highly optimized because you have people dedicated to developing this, and who have also been involved in development of CUDA and the GPU, so they know how what's going on in the background, so that they have a very highly optimized implementation. So usually the how people use it is that they use vanilla, the normal CUDA code for allocating memories, and they run the computations using cuDNN, and then they get back the data using CUDA. So this is a common use case that they do. So finally, we are almost near the end of the talk. So just to recap, it's all connected. So you have tensors for representing data, you have some text or images, you convert it into tensors, and then you run operations on them. So the general framework is like you have a 10 input tensor, you run operations on it, you get an output tensor. You have a computational graph so that it's clean, and then a computational graph as like computational graph will be like input. Oops, sorry. Computational graph would be like there's an input, and then there's first operation, second operation, third operation, and so on, nth operation, and you get the output. And then you have auto differentiation, which is a generalized backpropagation. And then you have and the backend BLAS or CUDA or cuBLAS or cuDNN implementation backends, which are used for getting the best performance. So this is all that there is in any deep learning framework. And like if you want, you can just open up, for example, say Torch, because I'm not giving you the examples for that, and then you can figure out like how it's representing tensors, or how what operations are there, and what the computational graph object over there, and you can find that there's a very good mapping between what I've discussed here and with what's implemented over there. So the next question is, from here, what do you do next? Well, you can, now that you know how things are implemented in the background, then you can explain that why your network is not training as fast as you expected. For example, if you wanted to, I see this kind of issues in Tiano's issue tracker a lot. People come and say, hey, I was running on a CPU, and I could run it on, I could train it. One epoch took say 10 minutes, and when I put it on a GPU, I was expecting at least 100 times speed ups, but I got like a 10x speed up only. So what's happening? So things like that, you are better able to debug the issues. And if you want to know more about exactly how these are implemented, you can take a look at their internal documentation, which details how they implement it. And I particularly found the Tiano's documentation to be pretty elaborate. I personally found that TensorFlow was a bit less elaborate, and I've not checked out the docs for Torch or PyTorch, but once you do go to the Tiano dev docs, it's you get to appreciate how much they've developed it. And if you want, you can make your own deep learning framework just for fun, and maybe it's pretty good, people pick it up. Maybe another small suggestion is, why not we make our own deep learning library as part of Idli? Let's call it Chutney, and let's say we could just do it for knowledge, and if people are interested, we could do it. So you can start it just only on CPUs. You can just write NumPy code for how you can run convolutions or sigmoids or LSTMs, and then if people are interested, we can go on to do the CUDA implementations as well. So it's up to you guys. Any questions? All right. So Jacob had one question on the stream. For fast computation, the computation graph operations must be converted to matrix operations for GPU. Is that right? Yes, it depends upon the operations. For sometimes like convolutions which are pretty fast on GPU when compared to CPUs. LSTMs sometimes not so much because like in a convolution you can see that the same operation is repeated over and over again. Like there's a sliding window and you do the same matrix operation. So instead of like doing it sequentially, like shifting it one by one, you could just tell the GPU to do it all the sliding together at the same time, and you get much better speed ups. LSTMs not so much because it's just an unrolling, and you need there's a dependency because you need the outputs of the previous time step to compute the next current time step and so on. So there's a dependency, and having parallelism does not help as much as say having parallelism and convolution. Okay, and continue as a follow-up, he asks, in that case, how is the forward propagation, inference, and backward propagations mapped to matrix operations for GPU? So, well, mapping to matrix operations is pretty straightforward. Like, I'll show you the like in this, for example, in this slide, we had the sigmoid layer being converted to matrix operations directly, and there's no special hardware matrix operations for GPU. You compute them, you convert them into matrix operations, which could be run either on CPU or GPU, and then sometimes to make sure that you can get as much parallelism as possible, you just change the ordering of the operation. For example, in matrix multiplication, there's a three layered loop, right? First you go through the rows, then you go through the columns, and there's a third row which computes the dot product. So sometimes depending upon the locality, you can shift over. Instead of going to the row first, you could do to the columns first, and then inside the columns you could have for each row. So that's more of a hardware specific implementation details, but a mapping from a convolution or a sigmoid operation to a matrix operation is pretty straightforward without worrying about whether it's a CPU that's running or a GPU that's running. Once you do convert it, then you need to optimize for the hardware. So that's a bit of an application specific issue, and that's not something that I could elaborate completely. But depending upon if you give me a use case of say if you want to do some operation on this hardware, how do I do it efficiently? So that's a long discussion to have. All right, so I've uploaded these slides on the Facebook event page, so you guys can check it out anytime you want, and I'll be there on the Italy group, and you can always ask me questions. And it's always nice to have discussions on the group. So if there are no more questions, then I can wind this up. But before I do, I should give credit where it's due, and I'd like to thank Malai for proofreading the article because I was discussing about these are so many things over there and people are not really aware of what's happening. Let's write an article about it, and he said, yeah, let's do it. And he after I wrote the article, he helped me proofread it, and as well as he helped organizing and moderating this talk. So thank you, Malai. And definitely to the Indian Deep Learning Initiative. It's a wonderful group, and there are a lot of awesome discussions. And it's one of the groups where I don't mind logging to Facebook to check it out. So that's a pretty cool thing, and I hope we can have more interesting discussions and have more people there. And finally, and also to Frederick Bastin, he's the Theano lead developer, and he was pretty helpful while I was starting out. He spent time with me to explain concepts and explain how they do things, and that's he took time to explain all of that. And I should obviously, and what I know, most of the things that I know, I started from there. He was the one who explained, okay, you should try this out or that, and so thanks. And also to Chris Ola, because most of the uh, most of the illustrations that I have here are taken from his blog, and he does very good, pretty good, and very explanative illustrations. So thanks. Of course, the deep learning community in general, like we cannot have such an initiative if the community in general wasn't open and wasn't willing to share ideas. So thanks for that as well. So thank you everyone for attending this talk. I'm very sorry for all the interruptions in the middle. It's my first time, so hopefully the next time I give a talk on topics, there won't be any interruptions like this. And thanks a lot for spending more than an hour with me listening to my talk. And if you have any questions or any follow-up ideas that you want to do, whether you want to go ahead implementing chutney, or if you want me to elaborate or have another talk on some particular topic, feel free to reach out to me. So thanks.